Saxon's Calculus, Lesson A, was about the real numbers, which we talked about in a previous video, and then a fundamental concept review, which is where I stopped partway through in the example. So this video is picking up with example 5 on page 4 and going through 5 through 10's examples. So example 5 is 2 with negative root 2 times another root 2 plus 3i root 2. So if you remember your eye chart, you know where this is headed. And another one of those. All right, so when I look here at this first set, I know that I'm multiplying, and this root 2 and this root 2 are going to make a 2, multiplying with this 2 on the outside, which is making a whole number of 4. But I did not deal with the fact that I had a negative in a root. And you need to remember that I stands for the square root of -1. So this negative inside the root turns into an I and goes here with my 4. And I see that I already had another I here, and there's nothing I can do with a 3, an I, and a root 2 that can't be simplified or changed. Minus, dropping down, and then here becomes my slightly tricky part. I think I might be able to do -2 times -2 and make it +4, but then I have eliminated these signs, and inside a root, what were they? Oh yeah, that's right, they were i's. So the I takes the precedent over multiplying and losing something. So this becomes an I when I pull it out. This becomes an I when I pull it out. Now I have just root 2 and root 2. And a set of those means I can pull a 2 out. Now that's completely the wrong order there. So technically, this should be -2, and then I times I is I squared. All right, 4i plus 3i root 2. There's nothing I can do with any of those parts. They're not like terms. This one doesn't have a root 2. This one does. They both have i's, but without them being identical, they're not like terms. My I squared, however, I can fix. Now, if you're remembering your eye chart from last year, you know that when you multiply this times another one of itself, so if you want to see that, that's root 1 times another root 1, you get the killing off of the square root, and you're just keeping the inner concept of -1. So that's what's happening here. This becomes a -1. -1 times -2 changes this to +2. So I still have that 4i plus 3i root 2. And this 2 is not a like term to any of the rest. It doesn't have an I, so none of these can go together. And that's as far as I can carry that problem. Now, in the book, they use the 2 in the front, and they choose to factor out the I and write it with an I parenthesis with 4 plus 3 root 2 in there. Either way is okay. This is my preferred method that you will see me use rather than leaving the I factored out. Now, example 6 gives us 2i squared minus 3i plus 4 over I squared plus 2i minus 1. So when I go to simplify, I recognize I squared is -1, so -1 times 2 makes this -2 minus 3i plus 4. Is there anything I can do in the denominator? Yes, I squared is -1 plus 2i minus 1. Now these two are like terms. They don't have the I, so -2 plus 4 is 2 minus 3i. And -1 and -1 are like terms, no I term. So that's -2 plus 2i. That's as far as I can carry it as far as simplifying, but I have an I in the denominator. Just like the radicals, we don't like i's in denominators, so we do what we did before. We change the sign, and we make sure we do the same thing top and bottom, because that's the equivalent of multiplying by a 1. So now let's distribute. 2 times -2 is -4. 2 times -2i is -4i. -3i and -2, +6i. and then negative times negative is positive. 3 times 2 is 6, and I times I is I squared. In the denominator, negative 2 times negative 2 is positive 4. And again, I'm not going to write it, but negative 2 times negative 2i is positive 4i, and then that's negative 4i. They cancel off just like we expect them to. And then the last term is positive times negative is negative. 2 times 2 is 4, and I times I is I squared. So up here in the numerator, I have a negative 4i and a positive 6i. They're like terms. And this I squared is negative 1, so it's making that negative 6. Now they're like terms. So negative 4 and negative 6 is negative 10. Negative 4i plus 6i is 2i. And then in the bottom, this becomes negative 1 times negative 4. So this is changing to plus 4. 4 plus 4 is 8. Can I reduce all of the numbers that are here? Yes, by 2. So that's negative 5 plus I over 4. Now, they separated that into 2 different fractions. I'm going to leave it in one fraction, just personal preference. If you do separate it, this is negative 5/4 plus 1/4 I, or plus I over 4. But the preferable, if you're separating it, is to do the fraction and then the I, because the I is being treated like a variable. All right, example 7. They have y to the x plus 3, y to the x over 2 minus 1, z to the a all over y to the x minus a over 2 and z to the x minus a over 3. Now, I don't have to write them in the parenthesis that they did. They put them there because they wrote the fraction sideways, and they wanted you to know that it was not just the a that was dividing by the 2, it was the entire x minus a concept. So when I wrote it, even though I wrote it more in fraction form, I went ahead and wrote it with the parentheses just because I was following what the book had. The other thing I want to point out is you will see me do a z with an extra tag in it. That is also a preference because I am avoiding the confusion with 2, or at least trying to. It's a European way to write a z. So whether you write your z's with that or not doesn't really matter, just explaining why I do what I do. So in this numerator, I see that I have 2 base y's, and when I am multiplying bases, I add exponents. That's the rule. So y, and then when I'm adding all of these together, this is an x, this is an x. This has a denominator of 2, so I would need to give it a same denominator and make that 2 over 2, because that's the same as 1. So 2 plus 1 is 3x over 2, and then my 3 and my minus 1 leaves a plus 2. And I can choose to make that one fraction. I might do that in the next step. And then at the moment, there's nothing to change my z to the a. Now, down here, no bases are the same, so I need to move these things to combine them with what's up here. So if I choose to move this one, when you change its location, you change the signs. So this is now going to be negative x plus a all over 2, and it's just one set of the signs. It's not the denominator sign as well that's changing. And then if I choose to do the same with the z, that becomes negative x plus a over 3. And now I can put these y terms together. And yes, I will go ahead and make this a denominator of 2, which is changing it to a 4. So adding, let's see, this has an x, this has an x. So 3x over 2 minus x over 2 is 2x over 2, and that's going to reduce to x. Let me triple check myself on that. 3 minus 1 is 2. 2 over 2 cancels off, just leaves the x. Yes. Then 4 over 2. I think I'm going to take that back to the 2. I'll check and see how they did it in a second. And this a over 2 has not been used. But because it was an a, See, I might have written that as 4 plus a over 2. I don't know that it really matters. Now we do need to put our z's together, however. So a does not have the same denominator, so let's make it 3a over 3. This has the a term, so 3a plus an a is 4a over 3. And then nothing changed my minus x over 3. So you know what? Let's just do minus x over 3 here. Now let me check their format and see how they actually wrote that. Oh, there's a part B. I think I'm looking at that answer. Goodness. So y to the x plus 2 plus, yep, they did write it this way. They just wrote it with that slanted fraction, and then there's z 4a over 3. Again, they wrote it slanted. Okay, they wrote it as separate minus another x over 3. Either way, we're obviously getting the same answer. Now that I see there's a part B in this one, we need to do x to the 3/4 is multiplying with the root of xy, and then we have an x to the 1/2 and a cubed root of x to the 4th. So the key here is to change all of these bases so that they have exponents that are fractions, and then we can put them together, because at the moment a square root and a cubed root are completely different things and cannot be combined. So I'm going to leave my x to the 3/4 alone for now. And this x has an implied exponent of 1, that is the numerator, and the denominator number is the implied root number of 2. Same thing happening with the y, exponent of 1, root number of 2. Then this x to the 1/2 is already there, no change, and now fix this one so it's x. It has an exponent of 4, and its root number is 3. Now it's all in fraction exponents, which I can combine. So x is here, 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 and here. All 4 of those, when I'm multiplying bases, I'm adding exponents. So I need to add each of those. So I see that I have numbers 4, 2, and 3 for denominators. So the common denominator will then be 12. So this one multiplies by 3, which changes to 9. This one multiplies by a 6, so this becomes 6. This one multiplies again by 6 and becomes 6. This multiplies by 4. 4 times 4 is 16. So now we're adding 9 plus 6, 15, plus 6 more, 21, plus 16, 37, over our common denominator of 12, and there was nothing to change the y, so it just kept its y to the 1/2. And there's our answer for that combination. That's example 7. Example 8. They give us 4a to the 3m plus 2 minus 16a to the 2m. When I look at this, I don't have the same exponents, but I do see that I share a number between 4 and 16. This gives me a clue that I'm supposed to factor. And example 8 also tells me to factor, which means I'm looking for what can I pull out. So what number can pull from 4 and 16? 4. Now this a to the 3m plus 2, and if you remember, you can automatically just do this step without writing it out. But if, as you're getting back into it, it's helpful to write that this a to the 3m means a to the m, a to the m, a to the m, that's 3 m's, and an a, that's your a squared, yes, plus 2, sorry. And then this one is a to the m, a to the m. So what is shared between them? Well, here's an a to the m, here's an a to the m. These were not, so this is what I can pull out. An a to the m twice, so that's a to the 2m. Now what got left? So I pulled the 4, nothing left for numbers. I pulled 2 of the 3 m's, or I can use this list. So a to the m is left over, and I didn't touch any of the rest, so the plus 2, they're still there. minus, now when I pulled 4 out of the 16, that left me with a 4, and I pulled a to the 2m, so there's no other variables left, so there was nothing else left with that one. So this is the factored out. Now, can I simplify that any further? Did they? 4a did I miswrite something? 4a 3m plus 2 minus 16a. Oh my goodness, I did. That was a 3m. Hang on a second. That is a huge problem. Okay, let's fix that then, because this had another a to the m, which meant that there was another set here, so I actually pulled out a to the 3m. Now, that means I don't have an extra m here. It's just a squared minus 4. Ah, yes, okay. Now, a squared minus 4 will factor again. That's why they have a difference. So this is not boxed. It's not our final answer. So this splits into 2 parentheses. A squared is a and a. There is no middle term, which tells me the signs must be opposite to cancel the middle term. And 4 splits to 2 and 2. And as a final double check, positive times negative is negative. So that's a match. That I can box as my final split answer. And now we match what the book gave us for theirs. Example 9. Again, there's an A and a B. So A is 8a cubed minus b cubed c to the 6th. Now, what you need to recognize about this one, and again it says to factor it, is that all of these can be written with an exponent of a 3. So this is our perfect cubes factoring. There was a formula that you memorized in trig class for this, but first, let's change all of these to have exponents of 3. So 8 is the same as 2 cubed, a cubed is in its cubed format, b cubed is in its cubed format, but c needs to be something cubed. So it's 1 base, 2 exponents implied here, so 3 times what gives me the 6? That's my 2. Now, the pattern that you memorized last year for perfect cubes said that the first parenthesis is to pull 1 piece off of everything here. So 2a minus bc squared. That's 1 pulled off of all of them. The second part is always much longer. It's in 3 pieces. The first piece is what is left over from pulling this away from the first term. So I've pulled 1 2 out, that leaves me 2 2's, which is 4. And I pulled 1a out, leaving me 2 a's. The first term, and I'm going to skip the middle term for now, and the last term are always positive. That was also part of the memorized rule. So now it doesn't matter what sign this was. The last term will always be positive. So we pulled off 1bc squared. We're going to write the leftovers. So pulling 1b away leaves me with a b squared. Pulling 1c squared away leaves me 2 sets of 2's. So that multiplies c to the 4th. The middle term is always this piece multiplied together and change the sign. So it goes to a plus and then put together 2abc squared. And that is how you do a perfect cube factoring. Oops. Now part B, they want to review that again. So they give you m cubed plus x3 y6. So again, I see that everything can be written with a cubed. So we're going to keep our m cubed plus x cubed and then change y to, again, 3 times what gives 6? 2. And then we pull 1 piece off of each for the outer parentheses. So that's an m plus an x and a y squared. And then our long parenthesis for our leftovers. What was left from the first term? 2 m's. Ignoring the middle for the moment, jumping to the end, it's always a plus. So 1x pulled out, leaving 2 x's. one set of the y's pulled out, leaving two sets, and y2 and 2 makes y to the fourth. The middle term is this multiplied together, change the sign, minus mxy squared. Again, the order that I would write those doesn't really matter as long as I have all of them in there. Now, I didn't double check, so before I move on, make sure I had no errors. M plus y squared, m squared, the minus, yes, all right. And finally then, example 10. Unfortunately, it's in three parts. They're reviewing three different things. So the first one is 14 factorial over 6 factorial and 11 factorial. Now, we liked these before. They were a lot of fun in trig class. So if you remember, factorials mean multiply with every number going down until you get to 1. You would never use the 0 because 0 times all that would undo all of it to 0. Now, I stopped here at 12 because the next number I would write is 11, but I see in my denominator I have an 11. So 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 would all cross off with this 11. So I'm just going to stop writing. Now, you can use the button on your calculator for factorials, and that's what most of you did last year. I tend to write them out manually and do as much as I can in my head. So this 6 factorial is still here. 6, 5, 4, 3, 2, and 1. And you will find on your calculator a little exclamation point that is your factorial button. Any combination that I see that helps me to cancel is what I'm going to do. So 4 times 3 is 12. 2 goes in here 7 times. Now 7 and 13 are both prime, so they're not going to reduce. So 7 times 3 is going to give me 91 over 6 times 5 times 1. The 1 is irrelevant. I can cross it off. So 6 times 5 gives me the 30, and I cannot reduce that down, so that is the answer. Now part B shifts gears and does summation notation. Is that fancy Greek looking E. The number at the top is the stopping place. The number at the bottom, where it gives you a letter and a number, is J equals 0 for this example. So it means you're going to begin with 0, plug in a 0, then plug in a 1, then plug in a 2, then plug in a 3, and stop. Now, what are you plugging it into? And they provide you the formula 2 to the jth power over top of j plus 1. And summation notation would indicate that you're summing, adding each of those answers together. So the first thing is to plug in the 0, 2 to the 0 over 0 plus 1, plus 2 to the first over 1 plus 1, plus 2 to the second over 2 plus 1, plus 2 cubed, and now we've reached the top one, so we know this is our last one, 3 plus 1, and then we work on simplifying it. 2 to the 0 is 1, 1 over 1 is 1, plus 2 over 2 is 1, 2 squared is 4, 4 over 3, 4 thirds, plus 8 over 4, which reduces to 2. Then we need to add all of those together, so 2, 3, 4, and 4 thirds is like another 1 and a third, so that's 5 and a third. You can either box the 5 and a third, or you can do what they did and keep that at 16 thirds. Either way, acceptable answer. And now finally C, which is another summation notation. And they start at I equals 1, and they go to 4. But there's not really a formula here. It just gave me a 3. So this means I have 3 plus, and that's implying I've turned it in the first time at a 1, then a 3 when I've plugged in the 2, then a 3 when I've plugged in the 3, and a 3 when I've plugged in the 4, and now I can stop. So 3 plus 3 plus 3 plus 3 is 12. So that's a super simple one. So basically what I would have shortcutted here when I realized I had no formula was 3 times 4 is 12, and I wouldn't even have bothered to write those out because it's going to be that same number. And then the only other thing I need to be careful of is if this had been a 2, I would have only done it not times 4 but times 3. So you just need to be careful that you you don't have a starting number that's other than 1.